Mr. Abbott, we're back for another boring activity explanation, this time for activity number 25 that we did in class today, changes in phase of water. We started with, snow. We put it in a beaker, we placed it on a hot plate, we heated the snow all the way from frozen solid snow to boiling water. We used a vernier temperature probe to watch it, and we generated a fairly nice heating curve from that. I'm going to go over the activity that you were given that corresponds to that. We're using data that goes a little bit farther, that's based on all the calculated values, so it should work, but hopefully we can move through this quickly. Now, on the vocab, I'm not going to go through all the definitions. The one definition I would like to talk about is latent heat. Latent heat is a form of potential energy. When they talk about latent heat, it's the energy either gained or lost during a phase change. So when you look at the properties of water chart, all the information that you need to know for liquid water for latent heat is in the box. Melting, freezing, vaporization, and condensation are all phase changes, so the number of joules that's required, the amount of energy in grams is listed. Some phase changes gain energy, other ones release that energy back to the environment, but any change in energy that occurs during a phase change is referred to as the latent heat. Now, on the bottom of the front page, you have this chart which essentially goes over, solid to liquid. You should know solid to liquid is melting, and that requires the addition of 334 joules per gram. Liquid to gas is vaporization. You could also call it evaporating. Okay, transpiration does the same process, but anytime liquid water goes into the gaseous phase, you have to add 2,260 joules per gram. Okay, so melting and vaporization is a gain of energy. When you do the opposite process, you're going to release that energy back into the environment. So gas to liquid is known as condensation. Okay, it's losing the same 2,260 joules per gram that was gained in vaporization. Liquid to solid, liquid water freezes. For liquid water to freeze, it's got to release 334 joules per gram, but you don't have to memorize it. If you want to picture the phases in order of increasing or decreasing energy, you can think of it as a ladder going from a solid to a liquid to a gas. You're gaining energy. You have to lose the same amount of energy to drop back down to the other phases. Now, the data table that we gave you is on the next page. For the data table, you'll see that there's 32 minutes of data. So we're starting at a temperature at time 0 of minus 100 degrees. And if you scroll all the way down to the bottom, you're going to get to the final temperature of 200 degrees after 32 minutes. So that would be going from solid, really cold ice to water vapor, completely gaseous at 200 degrees Celsius. Now, to help you set up the graph, we've got a graph here. The title, you need a title on the graph, and the title for your graph should be the heating curve of water. Okay, on the bottom, the independent variable is time in minutes, and the easiest scale to set up is there's 35 boxes, 32 minutes. Okay, each line is going to equal 1, but I would only label the dark lines every 5 minutes. Temperature has a wide range since you're going from minus 100 up to positive 200. The best scale is probably starting at minus 100, going up every line is 20. So you could label each dark line going up minus 100, 0, 100, 200, 300. Okay, as time goes on, the amount of energy that's being added is going to increase. So sometimes instead of labeling it time in minutes, they might say energy added in joules. But the basic, little diagram of this, we start with a certain mass of ice at minus 100 degrees. You're heating it with a Bunsen burner, you're heating it with a hot plate, whatever. You're adding energy, the same amount of energy each minute in joules, and we're watching what happened to the temperature. Once you plot the graph, okay, I will show you a completed graph for what this looks like, and we'll talk our way through each segment. So I plotted all 32 points. Okay, I've labeled certain other points to make it easier for us to discuss. So I put a point at every single step. So I labeled this from A to B. When the temperature is below 0, it's solid ice. So the slanted lines are the 3 phases. You go from solid to liquid to gas. The flat sections represent your phase changes. So for the first 2 minutes, you heated the solid ice up to 0 degrees. All of that energy was changing the kinetic energy. From B to C, any flat section is a phase change. But at 0 degrees, which is the melting point, you're adding energy, so going from B to C is melting. C to D is liquid only. Okay, when it's a flat section, you have 2 phases, but on the angles, it's a single phase. So when water is between 0 and 100 degrees, it's liquid water. And you'll see you should have had 4 minutes of liquid water only. Boiling or vaporization starts right at the 9-minute point, because that's when you hit 100 degrees. You'll notice that this is vaporization. It's a phase change, and during this phase change, which takes 21 minutes, all of the heat energy is going into breaking the molecules apart. You're adding 2,260 joules per gram to break those water molecules, those liquid molecules apart, and turn them into a gas. It wasn't until you hit that final 100-degree temperature at 32 that all of the liquid water evaporated and had been turned to water vapor. So the last 2 minutes, okay, from time 30 to time 32, you had 100% gaseous water vapor, and the temperature increased rapidly from 100 to 200. All right, the flat sections are the phase changes. One thing you may notice is that the slope of the slanted sections is not constant. Okay, looking at this, the liquid water is going to heat slower. Ice and water vapor seem to be heating a little bit more rapidly. Okay, if you do the calculations, this is 100 degrees in 2 minutes. So the solid appears to be going up 50 degrees Celsius each minute. The liquid water only changed 100 degrees in 4 minutes. So if I do the rate of change, 100 degrees divided by 4 would be 25 degrees per minute. So the liquid water is heating as you're adding the energy, but it's heating at a slower rate. This is a change that's caused by the specific heat of the material. So when we look at the reference tables, we're heating water as a liquid, which has a specific heat of 4.18. We're heating it as ice, which has a specific heat of 2.11, and we're heating it as water vapor, which is 2.00. So you'll see the ice and the water vapor heat at similar rates because they have almost identical specific heats. Okay, liquid water takes twice as much energy. It takes 4.18 joules per gram degree Celsius instead of 2 joules per gram degree Celsius. And that's why you have a change in the rate depending on which phase of water you have. You have to remember with specific heat, The higher the specific heat, the slower it heats. Lower values for specific heat actually heat more rapidly. So on this chart, lead requires the least energy to heat up. So lead heats fastest, but cools fastest. So we're going back to your graph. Your graph should look something similar to this. Okay, there's 3 slanted sections for solid, liquids, and gases. The temperature determines the phase. Okay, you should know that during a phase change, the energy that's added is called latent heat, and it's a change in potential energy. So what I recorded underneath, we color-coded the graph, and I've made this chart telling you what's happening in each time interval, which phases exist during that time interval, the process that happens, and then what type of energy change. When the temperature goes up, temperature is average kinetic energy, so a change in temperature gives you a change in kinetic energy. A phase change, the flat sections, is a change in potential energy. That chart is going to be really helpful in terms of you answering the questions. All right, the rate changes, okay, liquid water heats slower than ice or water vapor, but the majority of the time, actually 21 out of 32 minutes, was vaporization, because you have to add a huge amount of energy. Okay, 2,260 joules per gram is a lot more energy. It takes a lot more time to turn water from a liquid into a gas than it does to melt ice and change it from a solid to a liquid. Those numbers, 334 joules per gram is honestly called the heat of fusion. 2,260 joules per gram is the heat of vaporization, but at different phases have a different amount of energy. There's a change in potential energy between phases. We refer to that as the latent heat that's either gained or lost. So this chart should help you with doing the questions on the lab. Your graph should look something like this. You don't have to color code it. I just thought it would be easier to refer to them frequently on Regents questions. They'll label the points at the end of each segment, but that graph is always going to look the same. Whenever you look at a heating curve of water, melting is going to be at 0, vaporization is going to be at 100. Take care. Hope that helps.